Okay, so we have given this idea of a probability experiment as some event where the outcome is uncertain, and we have the idea of we're actually going to begin to build a model of these experiments that involves not just outcomes, but something called events and something called a sample space. And this is where set theory comes in. So this is a little difficult or a little bit unusual, is that what we're actually going to talk about is not the probability of outcomes, but the probability of an event occurring. Now, what is an event? An event is a set of outcomes. So what probability deals with are events and the so for example, if we had heads and tails in this simple case, there's only so many sets of outcomes that can occur. For example, we could have the set with just heads, and that would be the event where heads occurred. And then we could have the event where just tails occurred. We could also have the event where either heads or tails occurred. And then there's also the event where nothing occurs. So all of these sets are all actually subsets of a big set called the sample space. So the sample space of a probability experiment so the sample space of a probability experiment is the set of all possible outcomes, the set of all outcomes. So for example, for the coin, it would be this set here. So all events are subsets of the sample space of a given probability experiment. Okay. So let's look at, say, another one that's maybe a little bit more complicated. Let's say you had a dice roll. Well, the sample space for a dice roll is going to be using the names 1 through 6. For a usual dice, there's a sample space. So we have a lot of different events. For example, we could have the event where the result was even. Or the event where the face that showed up on the dice was odd. Or we could have that it was just less than 4. Like that, or less than or equal to 4. Okay, so we could make any subsets. Now, it's going to be important that we're going to allow any subsets to be outcomes. So we're going to include S as an event also, because S is a subset of itself, of the sample space. And the empty set is an event that never happens, because it's the case when there's no outcome. So you roll a dice and nothing happens. Well, that, by definition, that never occurs, because your idealistic experiment is always 1 through, you're always going to get this 1 through 6. So this is a convenience, because we know that the empty set is a subset of every set. So because that's true. We want to be able to have, because the idea here is, excuse me, that we'd like to be able to say, well, if we have two events, their intersection is going to be a subset of sample space, and we'd like that to always work. But what about the event? What about this? The intersection of the even and odd sample spaces that, well, it's going to be the empty set, right? Because there's no intersection between the outcomes in this even event and the outcomes in the odd event. Now, if this is the case, if the intersection of two events is the empty set, then these events are said to be mutually exclusive. And just as later on, we're going to see that this word mutually exclusive also came up when we were doing counting. We had a counting principle where we had choices, and there were mutually exclusive choices and there were independent choices. And similarly, while we're not going to talk about these, we'll talk about this later, but similarly, there's going to be events that can be mutually exclusive or independent, because basically our whole subject of probability is going to be based on counting. So all the stuff we've done in counting will reappear here in this context, because we're going to be counting the number of outcomes in different sets and different subsets of sample space. Okay. Now let's set, these are simple sample spaces, but what about if the experiment, if our probability experiment was tossing two coins? Well, if I have two coins, well, I could toss two coins one after another. I could either have two coins or one coin twice. Maybe it's simpler to think of one coin twice, because you can see on the first throw, you either have heads or tails. And on the second toss, you either have heads or tails. Well, we need a name for the outcomes of this probability experiment, so we're just going to stick these together. So the outcomes of tossing two coins these are the possible outcomes: heads, heads, tails, tails. That's like heads, both of the coins come with heads, both tails, or we could have heads then tails, or tails then heads. So that's the sample space. So generally, it's a convention of whether you have what the names are. Let's see, and then tails, tails. Okay, so and then now here we can begin to see that there's a different. It's going to be interesting to have the different numbers of outcomes in the sample space. So we're going to use the same notation for this is the number of elements in a set. So that's the same thing, has the same meaning here. So the size of this sample space of tossing, the probability experiment of tossing two coins, is 4. And the earlier ones would have smaller sample space sizes. Well, let's look at then another example of, say, two six-sided dice. Well, the outcomes of the first, let's say you roll one dice twice. So the first roll, you could have any of the 6 faces could be showing. So if we name the faces 1, 2, 3, 4, 5, 6, the first one could be 1 through 6. The second one could be 1 through 6. So we're going to write any outcome as 2 integers. Like, for example, 3, 4. We're not going to think of as the number 34. We're going to think of as the first toss was a 3, the second toss was a 4. So we want to read this as 3, 4, not 34. because we're not thinking of it as a number. We're just thinking of it as a name for an outcome. So our sample space then would be all of these pairs. We can't really, it's going to become sort of large at this point. We'd start off with 1, 1, 1, 2, 1, 3, up to say 5, 6, 6, 6. Now, so we begin to get sample space sizes that are a little bit large. And so it's going to be important to know how many elements are there. And so this again is like, you can sort of see that this outcome, the outcome of the first dice and the second dice are independent. So if I wanted to count how many elements are in this set, we would say, well, since these are 6 possibilities here and 6 possibilities here, they're independent. So this is going to be 6 times 6 equals 36. Okay, and I will have to revise this because I got this backwards. This page, let me put this page as 1 and this page as 2. And I'll rearrange that for the, okay. There, okay, and this page will be 3. Okay, so we have the basic ideas. Let me stop and start the recording.